Everything's loaded up. We're going to start where we left off yesterday on Calculus 2, a particularly annoying problem where I applied power reduction equations instead of separating out my cosines and sines and using some substitution instead. So we're going to go back to that problem, and then today is kind of just going to be a lot of Calculus 2. I have a test later this week, a lot of work that I need to get done, and yesterday the sessions for quantum physics, linear algebra, and Calculus 3 all went about twice as fast as I had scheduled them to go. I didn't think I'd get through that many lectures. So today's a Calculus 2 day, and in a minute we are just going to get started on that. So, get your study materials, make sure you have a tablet and pen, or your paper tablet and pen, your papers, drink, some food if you need it, whatever you need to focus. Go grab that in about 5 minutes. We'll get started with our studying. Alright, I have all of my stuff pulled up, so we'll get started in just a minute. But first, a brief word about studying, okay? So, as I'm streaming this, it is the summer. For me, it's the summer after my senior year of high school. So, why am I studying? I'm studying because, well, A, I have a summer class. I'm taking Calculus 2 over the summer. I didn't take it while I was in high school, which is pretty normal. Most people, you don't get to Calculus in high school. If you did, that's awesome. But getting ahead to me is important, because going off to college, something good to think about, is that you're there to learn skills, not get grades. So setting yourself up to learn skills is what's really important. So studying for me is a way to do that, to kind of maximize what I get out of getting a college education. If you are not going to college, or that's much later for you, studying is important regardless. Just learning is really good for your brain, it's good for your life, it's good for you, and it really doesn't matter what you're learning too much. You could be learning about English, philosophy, another language, or, like I'm doing here, math and physics, mostly. So, whatever you're doing, just stick to it and get good at it. Because if you are gaining a skill, then you're doing something really good for yourself. And with that, we are going to go ahead and start on today's work. Alright, first question. We are picking up where we left off yesterday with that ridiculous cosine to the 9th x. Now if you didn't watch yesterday's stream, I tried to use the power reduction formula multiple times to attack this integral. And that isn't a smart thing to do. Whenever you have an integral like this, you want to break off your cosines, make sines, and do some substitution. Just using power reduction formula is like using a common pump in Fortnite and not hitting any headshots on an opponent that's like full pot. It's not good. What we're going to do is a little bit smarter. So let's go ahead and start. What we're going to do is we're going to break off a cosine squared. So we're going to have cosine to the 7th x and cosine squared x. And right now we're just going to be manipulating the integrand, so I'm not going to rewrite the integral every time. So we've got cosine to the 7th x times cosine squared x, and we can change that to cosine to the 7th x times 1 minus sine squared x. Alright? So what we're going to do with that is we're going to start doing some substitution. Well, we're going to do the substitution in a minute. First, I need to figure out the general direction of the integral. Because while I am doing this class, I'm doing this all for the first time just like you, so not an instructor, I do get a little lost. So right here, we have 1 minus sine squared, we have a cosine 7th x, and then we have our dx. So what are we going to do? We're probably going to keep breaking off cosines and see what happens. Because what it looks like we can get it to, so we have this 5, or a 7 here, is get to cosine 5th x, and we'll just do 1 minus sine squared x squared, because we break off another one of them. And then cosine to the 3rd x times 1 minus sine squared x cubed. And finally, cosine x, 1 minus sine squared x to the 4th. Alright, now this is starting to look good, because if we do our u substitution, and we set u is equal to sine of x, then du dx is going to equal cosine x, which means du equals cosine x dx, if we do a little bit of algebraic manipulation. Right, so now what we have is 1 minus u squared to the 4th du, because this cosine dx is equal to du. And that sine is u. So now we have a new, much simpler integrand. We have the integral from 0 to pi over 2 of 1 minus u squared to the 4th power du. And let's see. Oh. Okay, normally I can't see chat because I have this open while I'm studying, but hello Morgan, thank you for joining. How are you? And there's a delay between when I say things, about 10 seconds, and when they actually get seen on stream. So, having said that, I'm going to work for 20 seconds. Okay, so we have pi over 2 to 0, 1 minus u squared to the fourth. We're going to do the dirty work and kind of expand that expression right there. So 1 minus u squared times 1 minus u squared, 1 minus u squared, 1 minus u squared. Okay. Now, first things first, we have our FOIL method, of course. We're going to go 1 minus 2u squared plus u to the fourth. That's times 1 minus u squared times 1 minus u squared. Alright. Now, oh, and I should start our 5010. Alright. Now we've got the timer started since I forgot. Ronvier, it's nice to see you. Yes, I am studying. I'm studying because I have a college class over the summer, taking Calculus 2, and I am kind of preparing for my degree work at Mines, just because the school is kind of known for having pretty rigorous, difficult coursework, so I'm trying to get ahead of the curve and make sure that I am ready for that when it comes. So, back to our integral here, we have 1 minus 2u squared plus u to the fourth times, this is the same expression, so we can obviously see that it'll also yield 1 minus 2u squared plus u to the fourth, and then we're going to expand that expression out. So we have 1 times 1, 1 times negative 2 to the u squared, 1 times u to the fourth. We have negative 2u squared times 1, negative 2u squared times negative 2u squared, which is positive 4u to the fourth, and then minus 2u to the sixth. Thank you, Ronvier. I will need that luck. And then for that last term, we'll have plus u to the fourth, so it's right there. Then minus 2u to the sixth, plus u to the eighth. Alright, now we're going to keep going with the algebra and just combine like terms. So let's see, our highest degree is an 8, so put u to the eighth first. We have multiple u to the sixth, so negative 2, so we'll say minus 4 u to the sixth. So we've taken care of those terms. I'm going to cross them out. We have 6u to the fourth, excuse me. So we'll cross those out. Minus 4u to the fourth. Have I just done something silly? Yes, I did, because I wrote u to the fourth instead of u squared. Minus 4u squared, apologies, plus 1. Alright, now that we have that expanded, we can break this up into multiple very, very trivial, simple integrals, which is nice. However, I'm just going to go ahead and keep them together. Polynomial integration is one of the, if not the simplest form, besides just like integrating a constant. So we should be able to push through this without too much trouble. So what we're going to have is u to the ninth over 9 minus 4 u to the seventh over 6 plus 6 u to the fifth over 5 minus 4 u to the third over 3 plus u. And I wrote dx instead of du up here. Let me fix that really quickly. Alright. Now we've gotten our actual result from the integration, but we still need to take that between 0 and pi over 2. So how are we going to do that? Well, we're just going to plug back in the value for u and then evaluate it. So we have sine of x is our u. So sine of pi over 2 to the 9th power over 9 minus 4 times sine pi over 2 to the 7th over 6 plus 6 sine of pi over 2 to the 5th over 5 minus 4 sine of pi over 2 to the 3rd over 3 plus sine of pi over 2. Alright, it's a really long expression, but it's going to simplify pretty nicely because, here we'll pull this up over here. So sine of pi over 2 is 1. So all of these places we have sine pi over 2, that's just 1. So we have 1 to the 9th over 9. 1 to any power is just itself. 1 times 1 times 1 will always be 1. So we have 1/9 minus 4/6, or 4/6 plus 6/5 minus 4/3 plus 1. Now, sine of 0 is 0. So we actually don't need to write out the second term, but we would write minus sine of 0 all to the 9th over 9, all of that stuff. But that's all 0, so we're just going to leave it out for time's sake. Alright, so we need to get all of these in terms of the same denominator so we can add them up. So let's look at doing that now. The easiest to start with is going to be our 1/9 and 4/3. So let's go ahead and do that. We have positive 1/9, negative 4/3. 4/3, we multiply both sides by 3, and we have 12/9, so negative 12/9. Now, negative 12/9 plus 1/9, we have negative 11/9. Now we are going to look at the term 4/6. So we want to get these, again, equal denominators. So what we're going to do is just multiply this fraction by 2 and this by 3 to get 18 on the bottom of both of them. So we'll have negative 22/18 minus 12 over 18. And that's going to give us negative 34/18. And then finally, we're going to add our 6/5 and our 1. So plus 6/5. So we need a common denominator again. In this case, I'm just going to multiply by each other instead of trying to find a smaller common denominator. So 5 times negative 34, the way I do it in my head, is 34 times 10, 340, divided by 2, which is 170. So we'll have negative 170 over 5 times 18 is 90, plus 18 times 6, this one is mildly more annoying, it's 108. Let me just double check that on the calculator. Sometimes my mental math isn't trustworthy. I wrote 18 plus 6 instead of 18 times 6. Was it? Yeah, 108. 108 over 90. So the difference between 108 and 70 is negative 62. Because it's negative 170 and positive 108. So negative 62 over 90. And then plus 1, which just means plus 90 over 90, means we have 28 over 90, which is 14 over 45. And I don't see a super obvious way to keep simplifying that, so we're just going to give that a whirl. 14 over 45. Incorrect. Alright. That's terrible. Well, it's not. Because all we have to do is take it again and be more careful. Oh, that's the thing with integration, is making one mistake early on can kind of cook you. But it's not too hard to correct. So let's go back and try this again. And we'll be a little bit more steady-headed in our approach. We have pi over 2 and 0. Those are our limits of integration. And cosine to the 9th x dx. Okay. So what are we going to do with this? Well, we are probably going to separate off a cosine squared. So we'll have our cosine, second time we've done that, cosine to the 7th x, 1 minus sine squared x. Now, what we're probably wanting to do is get this integral simpler, even. So how can we do that? For reference, it has been a minute since we did this form of integration. We had specific units, and then this is kind of an overview of all of them. So what are we going to do? Well, we can distribute and get cosine 7th x minus cosine 7th x sine squared x. That's one thing that we can do. Is it the most helpful? I'm not precisely sure. Let's see. I don't think that's going to be the way to go. So I liked what we had before, the simplification. I'm thinking it just must have been an error in calculation. Well, let's see. Okay, what I'm going to do really quickly is plug the result we got originally into a calculator, and we're going to see what the calculator spits out, because I have a strong feeling that the error was in my algebra, not in the processes that we took to finish the integral. So, you can't see it, but I'm typing this all into Desmos. And the answer is 14 over 45. But obviously that was not the correct answer. So let's see what's wrong. Could it be that? Hold on. Alright, well, as it turns out, whenever I wrote down 4 times u to the 7th over 7, I wrote down 6 instead of 7 in the denominator. And that was messing up the answer the entire time. So, yeah. But we got it correct, so moving on. Alright. Our next question is pretty much the same thing, but with a constant and using sine instead of cosine. So, we're still going from pi over 2, 0. This time we have 8 times sine to the 9th x dx. So, what are we going to do here? Same strategy. We're going to break off a bunch of cosines. So, we should end up with 8, 1 minus cosine squared x, and this should be to the 8th, or sorry, to the 4th. Sine x dx, u equals cosine x, du equals negative sine x dx. Negative is important. We put a negative in our integrand. So we have the integral from 0 to pi over 2 of negative 8, 1 minus u squared to the 4th du. And because we have the same form, I'm not going to go through the work of doing the expansion all over again. I'm going to come up here. I am going to copy what the expansion looks like and bring it back down. And then I'm going to recall that there is a negative 8 to distribute throughout all of that. So, let's see. We have negative, oh, and this is what we're integrating, to be clear. So we have negative 8 u to the 9th over 9 plus 4 u to the 7th over 7, not 6. Make sure of that this time. Minus 6 u to the 5th over 5 plus 4 u to the 3rd over 3. I've not been distributing that negative 8, so I'm going to go ahead and just leave it out here again. And then minus, well, there's a plus 1, so we'll do minus 8. So I have been distributing the sign of the negative. You'll notice all the signs flipped. So I'll go ahead and leave a positive 8 on the outside, and then this is all going to be between 0 and pi over 2. Now, cosine of pi over 2 is 0. Cosine of 0 is 1. So we already know that the first term, as in all of this with cosine pi over 2 substituted in, minus all of this with cosine 0 substituted in, is going to leave us with a negative 8. And the 8 distributes to the rest of that. We distributed the 8 here. It's kind of funky notation, but we'll let it be. So we have negative 8, and then minus, excuse me, we'll have negative 8 over 9 plus 32 over 7 minus 48 over 5 plus 32 over 3 minus 8. And negative 8 minus a negative 8 is negative 8 plus 8, so these cancel. And then we're just going to look inside right here. This is going to be our term. All of it is negative of the resulting thing. So we're going to punch that into a calculator. Alright, this is 1496 over 315, positive. We're taking the negative of that, so negative 1496 over 315. And let's test that answer. Let's see how we did. It says that is incorrect. So once again, I have made an algebraic error, and this is going to be a painful day. Okay. You know what, let's just take it from the top. I'm going to do this step by step. Thank you, Cooper. Alright, after a lot of tabulating, that was the correct answer. I had once again made an error typing it into the calculator that took more time to fix than it actually took to solve the problem. Thank you, Ryan, for the astute observation. Nerd is correct. Welcome, Jack Short. It's nice to see you. Alright, and my screen sharing has dropped again. Looks like the Remarkable is having some trouble. However, it does seem that we've come to an answer on this particular integral. So we are going to... Why does it keep doing that? Good lord. Okay. That's fixed now. We're going to plug that in and see if we have our correct answer. As long as we remember to type in our constant of integration, that is correct. All right. On to the next integral. Oh boy. Okay. What we have here is obviously an eligible candidate for integration by partial fraction. We have the integral of 2x squared plus 8x plus 2 over x to the fourth plus 2x squared plus 1. So what do? Well, let's go through it. Because we have a fraction of the form p of x over q of x, where q has a higher degree, meaning like 8 versus 6, we can decompose this into partial fractions. Now, actually decomposing this is going to be the tough part. So let's see what we can break this up into. It looks like we can break it up into x squared plus 1 times x squared plus 1. And just to check, we FOIL it. First, x squared times x squared, that's x fourth. 1 times x squared plus 1 times x squared, 2x squared. 1 times 1, 1. So we've decomposed it correctly for the first step. Now the trick is, can we decompose it any more than we have right here? And I think the answer is going to be no, but let's check. Because if this were a little bit different, we could do, yeah, okay. So if this were x squared minus 1, it would be a perfect square. We could decompose it into x minus 1 times x plus 1. It doesn't appear to be the case though. So you're going to work on that after the break. Okay, so this 10-minute break is a good time to get up, stretch your legs, get some food, get water, get some sunlight, whatever you need. Being stuck inside all day isn't great for you, and that is what I'm going to do. I'm going to go get some food and a drink, and I will be right back. I'm back, still in break time. Jack. I got myself a small burger, which doesn't sound like a snack, but it was a really small burger. And it's about lunchtime anyhow. And then some pretzel twists that are kind of spicy. They're pretty good. I think it's like a spicy mustard flavor. I don't know exactly what they are, but I can tell you more precisely later. Now for the rest of break, since we're actually on screen, I'm going to do something called guided drawing. I know that sounds ridiculous and silly, which is the same thing, but drawing or sketching in between work sessions can be super helpful for kind of, getting you back in the learning mindset, getting your brain freshened up. It helps you focus a little bit better whenever you go into your next work session. So for the remaining time, we're just going to do a little bit of sketching. And the goal here also is not to draw anything super specific or structured. I kind of just start with a random shape and see what it turns into. And that's kind of the fun of it. Alright, and that is time on break. So we are going to hop into our next work session. Right, and you can let me know in the comments if you would rather hear commentary on what I'm working on, or if you'd rather just listen to the rain and have the work in the background. Alright, by unanimous vote from Jack Short, it's going to continue being commentary. So let's jump back into the problem we left off with, good lord. And that's going to be this integral right here. Yes, integrate the polynomial. Thank you, Obamacare. So what we're going to be looking at is this x squared plus 1 times x squared plus 1. Now, we have two things, I guess we'll just call them things, that can't be simplified, and they aren't linear. If they were linear, they'd be a term just like x, or x plus 1. And that would be lovely, because then we could just do super simple integration techniques, but partial fraction decomposition isn't too hard. I do need to review what exactly you do whenever you have two terms that aren't linear, though. It's usually standard integral, you might have one, usually not multiple. Okay, it is what I thought it was, so let's jump into it. Normally, what you would do if you had something like x squared, x plus 1, is you would have a over x plus b over x squared plus c over x plus 1. If you have a term that isn't linear, say you just had x times x squared plus 1, you would have a over x plus bx plus c over x squared plus 1. Now what we're going to do here is sort of a combination of the two. So we're going to have in our setup ax plus b over x plus 1, x squared plus 1, and then cx plus d over x squared plus 1 squared. Alright, so this is our setup, and then what we do to start getting values for these a's, b's, c's, d's is we take 2x squared plus 8x plus 2 over x fourth plus 2x squared plus 1, which is just our integrand. We multiply that by x to the fourth plus 2x squared plus 1 to knock out the denominator. And then we go ahead and do the same to this right-hand side over here. Okay? So we know that this bottom is equivalent to x squared plus 1 squared. So what we're going to do is multiply each of these terms by that. So in this case, 1 of the x squared plus 1 squared will cancel, but we'll still have x squared plus 1 up here. And then this bottom will completely cancel, and we'll be left with cx plus d. Alright, let's arrange our terms. We are left with 2x squared plus 8x plus 2 equals ax cubed plus ax plus bx squared plus b. That should be an a, not an ax. Plus cx plus d. Now we're going to order this. So we have a times x cubed plus b times x squared plus c times x plus a plus b plus d, and that's going to be our integer at the end. Alright, so what have we got here? What we're going to do is we're going to match these terms to the coefficients on this side. So we have bx squared that needs to equal 2x squared. So from that we know b equals 2. We have 0 x cubed over here, so a equals 0. We have 8x, so c must equal 8. And then a plus b plus d is equal to 2. So let's take the values we know. In this case, a and b. We get 0 plus 2. So 0 plus 2 plus d equals 2. That's pretty trivial to solve. We can see d must also be 0. So d equals 0. So then we plug all of this information back into our original ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 squared, which now is going to turn into a is 0, 0 times x is 0, so we'll just leave it off. B is 2, so 2 over x squared plus 1. C is equal to 8, so 8x plus 0, we'll leave it off, over x squared plus 1 squared. And now we're going to integrate this right here, which is much simpler. So we have the integral of 2 over x squared plus 1 plus 8x over x squared plus 1 squared. Then we're going to break up that integral. So we'll have the integral of 2 x squared plus 1 plus 8x over x squared plus 1 squared. And I did mean to break that up. There we go. So there's our broken up integrals. Now, let's proceed from here. We have x squared plus 1 on the bottom. That looks like it might be a common integral form. So let me just check my cheat sheet. Yes, okay. So a squared plus x squared, in this case, where a is 1, the integral of that is 1 over a arctangent x over a plus c. So that's just a formula that you know, so I'll write that out here. And this is written in terms of u squared. That's just the variable that you are integrating with respect to. So if we have x and dx, that's the same as u and du. So this integral, super trivial. That 2 comes out front as a multiple, and we end up 2 1 over a is 1, so it's just 1, inverse tangent, or sorry, not inverse, arctangent, and then this is u over a, x over 1 is just x, so that's our first term, and we have a plus c, of course. Now, this one is going to be a touch more complicated. We're going to do a little bit of u substitution. So we have 8x, x squared plus 1 squared, and that is all fine and good. We're going to go to new terms, or new variables, with u equaling x squared, and du equaling 2x dx. So then we get the integral for u plus 1 squared du. Let me make it clearer that that is a 4. I hate drawing 4s like that, but it makes it more distinct from the u. So this is a lot easier to solve. But I'd still like to make it even simpler. So what we're going to do is have another change of variables where w equals u plus 1, dw equals du, and then we are left with 4 over w squared dw. So 2 layers of substitution to get it simplified all the way, but there it is. So the integral of 1 over w squared is negative 1 over w, and then 1 over w is 1 over u plus 1, and of course u is equal to x squared, so it's 1 over x squared plus 1 plus c. So if we bring everything down, we have 2 arctangent x minus 1 over x squared plus 1, all plus the integration constant c. So hefty integral, but we got through it. Let's see if we got it right. Alright, unfortunately, we did not get that right. We made some errors, so I'm going to have to go back and correct that. So, to do that, probably just going to start from the top. I'm going to do this a little bit more cleanly. Alright. Integral 2x squared plus 8x plus 2 over x to the 4th plus 2x squared plus 1 dx. Break it up. X squared plus 1 squared is what we can rewrite this as. So we have integral 2x squared plus 8x plus 2 all over x squared plus 1 squared, which yields ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 squared. Now we're actually going to solve it again, and we're going to have 2x squared plus 8x plus 2 is equal to ax plus bx squared plus 1 plus cx plus d. Alright. Now we're going to go ahead and distribute along this term and equate coefficients. Squared plus 8x plus 2 is equal to ax cubed plus ax. That's where I made my error earlier. I changed ax to a. That almost certainly threw the entire thing off. Bx squared plus b plus cx plus d, which gives us a times x cubed plus a plus c times x plus, oh, well, did a little bit out of order. Skipped our x squared, but I can just shift this to the right, and it's not a problem. B times x squared, a plus c times x plus d, d plus b, rather, for our flat integer. Now, a is still equal to 0 because we have 0x cubed over here. B is equal to 2. A plus c is equal to 8. We know a is 0, so c must equal 8. And then d plus b equals 2. Now we know b is equal to 2, so d must equal 0. And these are indeed different values than what we had before, so that is going to change the result, obviously. So let's take our ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 squared, substitute values in. So we'll end up with 2 over x squared plus 1 plus 8x over x squared plus 1 squared, and is, let's see, so that isn't actually incidentally different than what we had before. So that's a little concerning, but perhaps the error was in the integration, not splitting up the partial fractions. Let's see. So integral 2 over x squared plus 1 dx plus integral 8x x squared plus 1 squared dx. Alright, now first things first, we're going to sub in some values for this first integral, and then we'll sub in this second integral. For now, we'll just extend it down there. Let's work on this. If u equals x squared, du equals 2x dx. So we'll get the integral 4 over u plus 1 squared du. If we use our previous trick and substitute again, Rebecca Clark says she is going to judge my math harshly. Rebecca, please don't. You know what, actually, please do. But if I'm goofing up too much on this stream, you should go over to my linear algebra and calculus 3 streams and watch those, because I was doing pretty good there. So W equals U plus 1, dW equals du. Let's write that properly. So, and make it more obvious, this is a 4. My 4s look like U's. We should have integral 4 over W squared dW. Thank you, Rebecca. Alright, now, shouldn't mess up the integral of W squared too bad. The integral of W squared, we'll just write it out to be safe. It's the same 1 over W squared as W to the negative 2. And then we just have W to the negative 2 plus 1 over negative 2 plus 1, or W to the negative 1 over negative 1, or negative 1 over W. Alright, and of course we have a 4, so it'll be negative 4 over W. But W equals U plus 1. So really, we have negative 4 over U plus 1. But U equals x squared. So we really have negative 4 over x squared plus 1. Holy moly. And then we know that x squared plus 1 is of the form x squared plus a squared, or a squared plus x squared. So that's like 2 integral 1 over 1 squared plus x squared dx. And it is a general rule that integrals of the form integral 1 over a squared plus x squared dx yield 1 over a arctangent x over a plus c. So we're going to go ahead and apply that, and we end up with 2 times arctangent x plus c. So bring that all together, and we have that the integral of 2x squared plus 8x plus 2 over x fourth plus 2x squared plus 1 dx is equal to 2 times inverse tangent x minus 4 over x squared plus 1 plus the constant of integration c. Alright, now we're going to type that in and give it a whirl. Yeah, okay. So this is a lesson in being patient and careful whenever you're doing algebra. For the past 3 questions, the vast majority of the difficulty has come from me missing something or miswriting it. So I had the correct answer actually, but you'll notice that this 4, I kind of forgot to bring it down previously. That's why the answer showed up as wrong whenever I typed it in. I didn't carry a 4. So be careful about those little details. The devil's in the details. Alright, on to the next integral. It looks like we're going to have a candidate for trigonometric substitution here. So we have integral square root 64 minus 4x squared. So why did I say that this looks like a candidate for trigonometric substitution? Trigonometric substitution, good lord, it's hard to say fast. That's because it looks like we're very close to the form square root a squared minus x squared. Which, if I remember correctly, is a sign to do a sign substitution. I believe a squared minus x squared calls for x equals a sine theta. But we have a 4 in the way. right? So we need to get rid of that. Now, is 64 divisible by 4? The answer is yes. Yes, it is. But what number we will get if we divide out by 4, that I am unsure of. So let's go ahead and rewrite this as 4 times 64 divided by 4. I've been messing up mental math too much today. I'm just going to go ahead and type that into a calculator. That's 16. Okay, which is good news, because that leaves us with 16 minus x squared. That's actually wonderful news, because 16 is also a perfect square, 4 squared. So we still have our 4 squared times x squared. However, we need to get that 4 out of the expression. And we should be able to do that using a pretty simple strategy. Let's see. Alright, just had to look it up to double check. But it is indeed true when you have the square root of a times b, you can rewrite it as the square root of a times the square root of b, or rewrite this as the square root of 4 times the square root of 16 minus x squared, which gives us 2 times the square root of 16 minus x squared. Or, the form we're really interested in is 2 times the integral of the square root 4 squared minus x squared, because when we have that form, we know that it is time to do trigonometric substitution. And I am 99% sure that's sine. Yes, and that is correct. So now we will sub in x equals a sine theta, which is going to be super useful, and you'll see why in just a second. So a in this case, since we're looking at the form a squared minus x squared, is 4, because we have 4 squared. So x equals 4 sine theta. Dx is going to equal dx d theta is going to equal 4 cosine theta. So does that mean that means dx equals 4 cosine theta d theta? And that'll be important in just a moment, because we are going to say that we now have the integral of 4 squared minus x is equal to 4 sine theta, so x squared is 4 squared sine squared theta, or we have 2 times the integral, and I am getting messy with my notation, I apologize, but 2 times the integral of the square root of 4 squared times 1 minus sine squared theta, which can be obviously rewritten as 2 squared times 4 squared cosine squared theta, which can be rewritten, doing a lot of rewriting, as the integral of 4 cosine theta. And we have to bring down our dx, which we know is equal to 4 cosine theta d theta. So we have 2 times the integral of 16 cosine squared theta d theta, or 32 times the integral cosine squared theta d theta. And of course, whenever we have a cosine squared, we are going to be interested in a power reduction formula, or in this case, a half-angle formula to reduce cosine squared to something a little more integrable. Tough word. Integrable. Cosine squared theta is equal to 1 plus cosine 2 theta over 2. So we're going to loop around here, keep using this portion of the screen. 32 integral 1 half plus cosine 2 theta over 2. And I immediately broke up the fraction because we are wanting to make this simpler to integrate. So this just makes it easier to look at. So we have 32 times 1 half theta plus the integral of cosine 2 theta is 1 half sine 2 theta. That's over 2, so 1/4 sine 2 theta. And then that's going to be all plus c. But now we have to do some distribution and substitution. So let's get on it. 32 times a half is 16. So we have 16 theta plus 32 times a fourth is 8. 8 sine 2 theta, all plus c. Alright, so let's see what we do with these. Well, x equals 4 sine theta is where we're going to get our value for theta for. So if x equals 4 sine theta, then x over 4 inverse sine, or arc sine, is equal to theta. So over here we have 16 times arc sine x over 4. But we also have 8 sine 2 theta. So what is sine of 2 theta equal to? Now that one is actually going to take me a second too. Or it would if we didn't have a double angle formula to simplify this even further. Because sine 2 theta is equal to 2 sine theta cosine theta. So we can write 16 sine theta cosine theta, which is the 2 sine theta cosine theta times 8. And now we just have to take our values for sine theta and cosine theta and sub them in. We know that sine theta equals x over 4. So we have plus 16 times x over 4. Now, let's see what our value for cosine theta is. And we're going to do that by drawing a triangle here. So sine theta, sine, SOHCAHTOA, opposite over hypotenuse. We have x over 4, which means this is the square root of 4 squared minus x squared. So what we really have is 16 arc sine x over 4, excuse my terrible handwriting, plus 16 times x over 4 is 4x, times the square root of 4 squared minus x squared, plus, the constant of integration c. There's our answer, and now that we've gotten that, let's plug it in and see how we did. Alright. 16 inverse sine x over 4 plus why did I say C's full government name? That is because, I don't know why. Probably because I normally don't take regular calculus classes. I take them online and study mostly myself, so I call everything by its full name a lot of the time. Okay, well, we did not get it right, but the software has informed me that trigonometric substitutions are the correct thing to do, so we are going to attack it again and see what went wrong. C as in the integration constant. Now, we have the integral, the square root of 64 minus 4x squared dx, which means we have the integral of the square root of 4 times 16 minus x squared. A screenshot of the work that I've done on the tablet, if you'd like to, sure. Alright, which leads us to the integral of 2 square root 4 squared minus x squared. So x is going to be 4 sine theta, and dx d theta is going to equal 4 cosine theta. So dx equals 4 cosine theta d theta, which leads us to the integral of 2 times the square root of 4 squared minus 4 squared sine squared theta, 4 cosine theta d theta. I'm going to take that over and get the integral 2 square root 4 squared times 1 minus sine squared theta, 4 cosine theta d theta. And I know it's repetitive to write out the whole long thing, but it is helpful to keep track of everything and make sure you don't leave any loose ends. So 2 4 squared cosine squared theta, 4 cosine squared theta, not squared, just theta, d theta, leads us all the way back to 2 times 4 times cosine theta times 4 times cosine theta d theta, which leaves us with 16 cosine squared theta d theta as our integrand. Alright. What do we do with this? Well, we try to make it simpler. So cosine squared theta is equal to, I believe, 1 plus cosine 2 theta over 2. Yep, that is correct. So we're going to take that and we are going to rewrite our integral. So it's going to be the integral of 16 times, and we'll just go ahead and take the 16 out, 1 plus cosine 2 theta over 2 d theta, which is equal to 16 times the integral 1 half d theta plus 16 times the integral, 16 over 2, cosine 2 theta d theta. Now that brings us back around to 16 times 1 half times theta plus 16 over 2 times a half times sine 2 theta. A little more substitution to go. That leaves us with 8 theta plus 16 over 4 is 4. 4 sine 2 theta, where sine 2 theta is Rebecca, have you actually gotten your calculus teacher in the chat, or is this a friend and I'm being pranked? And I do apologize to chat for these slow reactions. I have low latency on the screen, which basically just means there is a long delay between what I say and when you hear it, about 20 seconds. So sir, I am working on this integral up here, on the top left-hand side of the screen. I've laid all my work out pretty neatly, so if you'd like to just take a look at it and let me know if you see any errors, that would be super helpful. Thank you very much. Right now, what I'm arriving at is 8 theta plus 4 times sine 2 theta, where I'm substituting in 2 sine theta cosine theta, so 4 times that is 8 sine theta cosine theta. And then I'm basically just going to substitute in the values for theta and the two trigonometric functions and see if I've fixed the error I had before, which I believe the problem was, yes, I put 8 where I needed a 4. This time you can see that I have the 4 there. I think it was an algebraic error, because theta should still equal inverse sine of x over 4, because, yeah, x equals 4 sine theta, which should leave us with 8 inverse sine theta x over 4 plus 8 times x over 4 and then cosine theta, and get the solution really quickly. If sine theta is x over 4, cosine theta should be square root 4 squared minus x squared. So this should be our answer right here. Four times 2. Did I put that in somewhere? Yes, I did. That's a pretty bad error. Thank you, Mr. Thack. If I'm pronouncing that wrong, please correct me. Holy moly. So that should be 32. I'm going through and correcting that. Rebecca, thank you for jumping in on that. So 32, half, 16, 32, over 2 again, 16/8. So we should have a 16 here. And we should have had a 32 over 2, so a 16 over here. Which means we should have 16 inverse sine, or arc sine, x over 4, plus, if this is a 16, need to draw that down correctly. 16 sine theta cosine theta brings us to 16 x over 4. Thanks for that. 16 over 4 is 4. So 16 arc sine x over 4 plus 4x square root 4 squared minus x squared plus the constant of integration c. Big catch by Mr. Thack. Thank you very much. So that is the biggest error I usually make, is algebraic. However, it still looks like I have the wrong answer here according to the software. So we've corrected our 4 times 2 times 4 is not 16, it's 32. Thank you, Mr. Thack. Right, we're going to keep working at this integral until we've got it right. I've probably made another silly error somewhere in here. Mr. Thack already caught a few of them. Thank you, Rebecca and Mr. Thack, for the assist. But let's get this integral fixed up. What is wrong with it? Rebecca Clark, I had a strong feeling that that was the case, because I didn't think a teacher would use the word punk or join a YouTube live stream of a friend of their student. But props to your friend for keeping up the facade. Now, Rebecca, if you'd like to take a crack at this integral, and by that I mean please take a crack at this integral, I should see if you have any better luck. So it seems like the value we're taking for cosine theta is actually... Oh, of course it's not. I've been taking cosine theta to be square root 4 squared minus x squared. It's obviously adjacent over hypotenuse. It's that over 4, which would cancel with the 4 here, which means it should just be x, and then we will have the correct answer. And that was the case. Okay, integral solved through a few ridiculous algebra errors. on to the next question. All right, we are once again dealing with a power of sine. So we're going to be taking the integral of 7 sine squared 3x dx. So first thing that I'm looking at doing is a half angle formula. So sine squared theta is equal to 1 minus cosine 2 theta over 2. Of course, we can do that with x's as well. So let's see what happens. We have 7. I'm going to take that out of the integral since it's a constant. We're going to take 7 times 1 minus cosine 6x over 2 dx. We're going to break up that integral, so 7 times the integral of 1/2 dx minus 7 times the integral of cosine 6x. We'll take out that 2 dx. Both of these are pretty trivial integrals. Will be 7 1/2 x minus 7 halves times 1 over 6 sine of 6x dx, not dx, plus c. The government name being the integration constant c. Now let's fix this up a little bit. We should have 7 over 2 times x minus 1/6 sine 6x plus c. Now let's plug that in. Rebecca, I understand that you are upset about doing trig integrals. However, this is a larger assignment. It's called integration strategies. So if you get through the integration via trigonometric tricks, then soon enough we'll be doing integration by parts. Had you gotten on the stream earlier, you actually would have seen some integration by parts. And it looks like we are actually going to be doing that right now. Maybe this is integration by parts. I'm not actually precisely sure what strategy we'll take. But we're going to use that strategy after a short break. All right, we have a bit of break left, so we'll take this time to answer any questions that anyone has. Anyone being two of you, so congratulations. Rebecca said, Coolio channel and you're Rebecca Clark's calculus TA. Very cool. So you TA calculus 1 and 2, or do you do the whole calc track, like calc 3, differential equations, partial differential equations, all that stuff? And then Rebecca, you said you never learned the tricks for trig. You took calculus BC. I don't know why you don't know the tricks. That seems like a skill issue, to be honest. Ran out of time? Rebecca, I don't know what you mean by ran out of time, but Diffie or multi? Well, if you'd like to tune in daily to my multivariable calculus series, it could be very easy to do multi next year. Now Jack Short says shame. Not too much shame though. Calc is hard. Well, not that calc is hard. Calc requires a lot to memorize. The trig in particular is frustrating though. But the question we'll be starting on with whenever we are over with break is integration by parts. Rebecca, thank you for bringing your teachers to help me on stream. Coolio channel taught multi. Okay, very nice. Well, Coolio, if you wouldn't mind tuning in to my multivariable series tomorrow and other days, you should definitely do that. But you must now depart, so have a wonderful day, Coolio channel. Thanks for stopping in. And best of luck with your TAing. Rebecca, T-minus 2 minutes until we do a integration by parts question. It looks like the homework software heard your pleas for something other than trig tricks, and it granted you that. So, the short remainder of break, I'm going to go back to doodling. I'm going to work on this doodle that I was messing with yesterday. kind of weird looking river, I guess. Why is it pink? This is pink because there is not a harsher red. This one in particular. This isn't really anything in particular, though. This is kind of just shapes and lines that I draw during break. Welcome, Blah, the calculus classmate. Nice to see you. You've caught us on break, but in a few minutes, when that timer runs up on screen, we are going to be hopping into some Calculus 2. If you'd like to review integration by parts, that's our next question. Right now, we're doing some artwork. We've got very little time left. Alright, and that's break. Blah says hip hip hooray, and thank you. I try my best with the artwork. It's been a while since I did art for any sustained period of time. So Blah, we are hopping straight into integration by parts. I'm glad you're excited. So we're looking at taking the integral of x times 20 to the x. We have a exponential and a polynomial. Luckily that makes it pretty easy to pick u and du, or u and dv rather. So u will be x, dv will be 20x dx. So our du will just be dx, and our v, does anyone want to guess what v will be? I have to respond to a message from my mother. Alright, that's all good. Alright. We have here exponentials are pretty simple. It's just going to be 20 to the x times, or not times, over natural logarithm of 20. So there's our v. Now we know generally we have the form integral u dv equals uv minus, not plus, the integral of v du. So we've set our u, v, dv, and du values. We're going to say our integral x times 20 to the x dx is equal to x 20 to the x. Have I learned the tabular method? If you're talking about like DI tables for organizing your dv's, v's, du's, and u's, I have, but it's been a while since I used it. Welcome x3 prime. How are you? Right. And we have the integral of 20x ln 20 dx, which isn't looking much simpler. So let's see if we've gone wrong here. Okay. So, going to take our expression, since it looks a little bit more complicated than I would like inside of that integral. I'm going to try and simplify that a bit. Well, actually, no it doesn't, because ln 20, you're Rebecca's graphing calculator for calculus. That is wonderful. How do you like being a calculator? So, I thought this looked scary because I thought I had an x on the bottom here. This is really just x, 20 to the x, ln 20 minus 1 over ln 20 integral 20 to the x dx. The integral of 20 to the x dx, pretty trivial integral. This is one we would have a formula for. So we have x, 20 to the x, ln over 20 minus 1 over ln 20, or natural logarithm 20, times 20 to the x over ln 20. X3 prime says, I love it, it's so fun. Well, I'm glad you enjoy it. I wasn't sure if you would, since, you know, being a graphing calculator seems kind of boring. Especially Rebecca, she makes so many mistakes on the calculator. It can become so frustrating. But I'm glad you can bear through that, because she's better than I am. So we're going to simplify this a bit. This will be 1 over ln 20 times x times 20 to the x minus, in this case, it'll be 20 to the x over ln 20 still, because we would have had that squared. Syntax error for this equation. Yes, Rebecca, we all make mistakes. No need to be offended. I did say I make more, which is true. X3 prime says, I think you've done that problem wrong. It's receiving from the motherboard that there is a syntax error for this question. Well, not everything can be done on the graphing calculator, unfortunately. But, good try. Thank you for the assist. It looks like we have this question down to an answer. So let's go ahead and see what happens if we plug that in. Because, much like Rebecca, I lose most of my points on tabulation errors while I'm working. But it looks like this is a pretty solid answer. And I was correct. That is the correct answer. So on to the next integral. And welcome Neo, Rebecca's Delta Math account. Forgive me, Neo. What is a Delta Math account? Oh, and I apologize, Rebecca, we are back to a trig integral, unfortunately. We're going to be taking the integral of 49 times tangent to the 5th x times secant to the 4th x dx. X3 prime coming in with the existential crisis. I am Rebecca's graphing calculator. What else do? I only calculate. X3 prime, don't worry about it. Calculation takes you far enough. You are a valuable calculator. I'm sure Rebecca appreciates you very much. So keep up the great work. Alright, so what we have here is kind of my least favorite kind of trig integral. I am the worst with my tangents and secants, but we are going to do our best. So what I believe this is going to come down to is 49 times secant fourth x, tangent fourth x, and then a broken off tangent x dx. If we set u equal to secant x tangent x, the derivative of that is, I believe, equal to tangent x, but I need to check my formula sheet to be sure. So let's see. The integral of secant tangent x is secant x, but that is not what we want to do here. Uh-oh. So let's confirm a few things. First, the relationship between secants and tangents. If I remember correctly, tangent x plus 1, or tangent squared x plus 1 is equal to secant squared. Is that correct? Okay, let's see. Okay. Neo, you are absolutely correct. Your professional opinion is spot on. We are looking to simplify more. Alright, so we do have the equation tangent squared x plus 1 is equal to secant squared x. Welcome, Xenotic. Rebecca Clark's AP exam. Xenotic, I have a question for you. How did it feel to have a 3 on you? I'm sorry to hear that, Xenotic. And to be clear, I was just joking. I'm poking fun at Rebecca. I'm sure you both did great on AP Calculus BC. 5s all around. Okay, Xenotic is following x3 prime with a existential crisis over their state of existence. So I will leave that to chat. Rebecca, console your test. Okay, so what are we looking at here? We probably want to break off some secants. Okay. Rebecca, please console your test. Xenotic is having a breakdown. Alright, let's see. Okay, what it looks like we're interested in doing is setting secant for x Oh, I see. Okay. We've got this backwards. If we set u equal to tangent x du equals secant squared x, so we're wanting to leave all but a secant squared. Rebecca, you need to take better care of your calculator and test. Okay. So we're going to have integral 49 tangent squared plus 1 tangent fifth x secant squared x dx. So when we set u equal to tangent x and du equals secant squared x, we will end up with integral 49 u squared plus 1 u to the fifth du. So that is going to leave us with 49 times the integral of u to the 7th plus u to the 5th du, which is a very trivial integral. 49 times u to the 8th over 8th plus 49 u to the 6th over 6 plus c, where u is tangent x, so 49 tangent x to the 8th, 8 plus 49 tangent the 6th x over 6 plus c. x3 prime, good calculator pun, I appreciate that. Alright, now we are going to see how we did on this answer by plugging it in. Alright, that is correct. So we are on to the next question. You're evaluating the integral. Oof. This is kind of rough looking. Integral of 9 times cosine of 9 square root x. Yeesh. Okay, so let's see what we can do about this. I think we're going to use u substitution here. We're going to see how that goes. We're going to set u equal to 9 square root x. Du dx will be, well, should be negative 9 over 2 square root x, I believe. Yeah. Where square root x equals u over 9. Which means du equals negative 81 over 2u dx. Welcome in, Linda Nelson, Rebecca's pre-calculus teacher. You said you knew she was destined to fail. Is there any reason you just didn't do a better job teaching her? Alright, so we should have 9 times 2u over negative 81 times cosine of u du as our resultant integral. Zenotic, we're looking at Linda Nelson's birthday. Alright, happy birthday, Linda Nelson. Congratulations on surviving the year. And hopefully many more to come. Alright, we've gotten this down to the integral of, or 2/9 times the integral of u cosine u du, which is a pretty lovely place to be. We just need to figure out how to integrate from here. So I am a little fuzzy on what exactly we should move on to. X3 Prime, make sure you go get a good charge. It was nice to have you. Have a nice day. Linda Nelson, I tried my best to teach her. It was a struggle. No, I get it. She's kind of a handful sometimes. Welcome, Joseph Imhoff. You are Rebecca's calculus homework. Little hospital, am I right? Yes, that is actually my hospital. I own that hospital. Alright. Now that we've gotten here, we're going to do some integration by parts. So we are going to have 2/9 times the integral u cosine u du, which is a super simple one. And that is going to equal, hold on, let's shape this up. If this integral is equal to this other side, 2/9 times it is equal to 2/9 times this other side. But let's pick our u and v. Let's see. Trigonometry is usually the first thing to go for dv, so we'll set dv as cosine u, and u is equal to why don't we use W and V since we already used U sub? I U du. All right. So then dw will equal du. Oh, hold on. I think I'm messing this up a little bit. Let's set up our table better. Oh, I'm going to come back up a little bit, or a lot of bit rather. All right. Alright, so we finished setting up our integration by parts table. So let's go ahead and write it out. U sine U minus integral. And since we started out with W dV is going to be V dW. So sine U du. Which basically means we're just going to have the integral 2/9, or have the result 2/9 u sine u minus the integral of sine u is negative cosine u. So it'll end up being plus cosine u. Two negatives make a positive, plus c, bring our 2/9 over, and then we'll sub in our u, because our u, where did we write in its value? All the way up here is, oh, that's the previous problem. Our u for this problem is 9 square root x. So 2/9 9 square root x sine 9 square root x plus 2/9 cosine 9 square root x plus c. These 9's cancel to 2 square root x sine 9 square root x plus 2/9 cosine 9 square root x plus c. And that should be our final result. So we're going to type that in and see how we did. And that is correct. Love to see the green pop up on screen. Next, we have another eligible bachelor for integration by parts. Rebecca, are you happy now? We're going from 0 to pi over 2 for e to the negative 10x times cosine x dx. Alright, let's see how this goes. Our u, in this case, is going to be e to the negative 10x and Rebecca is celebrating the integration by parts. I'm glad you're happy. Okay, so we have our integration by parts table set up. Now let's go ahead and write everything down. So this is going to equal VU, or UV, which is e to the negative 10x sine x minus the integral of v du, which is sine x, well, in this case, negative 10 e to the negative 10x sine x dx. Now it looks like we're going to do this again until we get the original formula and kind of do some interesting math. I'll show you when we get there because it's easier to say than it is to, or easier to show than it is to say. So we have that integral, but what does this integral equal? Well, we're going to have e to the negative 10x sine x minus u, once again, is going to equal negative 10 e to the negative 10x du is going to equal 100 e to the negative 10x dx. dv equals sine x dx, v equals negative cosine x. So let's write out what this equals. We're going to have 10 e to the negative 10x cosine x, the negative on the cosine and the negative on the exponential cancel. And then we're going to have minus the integral of v du, or 100 times the integral of e to the negative 10 for x times, this is v du, cosine x dx. In this case, the negative cancels out here, so this is going to be a plus, which means at the end of the day, we have the integral from 0 to pi over 2 of e to the negative 10x cosine x dx is equal to e to the negative 10x sine x minus 10 e to the negative 10x cosine x minus 100 times the integral from 0 to pi over 2 of e to the negative 10x cosine x dx. Which means that, if we do a little bit of algebra, 101 times the integral of pi over 2, 0, of e to the negative 10x cosine x dx is equal to, good lord, e to the negative 10x sine x minus 10 to the e, or 10 times e to the negative 10x cosine x. We divide out. Rebecca says, did you dress up for this live stream? I don't really consider it dressing up because I have my sleeves rolled up. But I just put on a shirt. Which means the integral from 0 to pi over 2 of e to the negative 10x cosine x dx is equal to e to the negative 10x sine x minus 10 times e to the negative 10x cosine x. I'm getting sick of saying that. I'm sure you're getting sick of hearing, getting sick of hearing it, divided by 101, all plus some integration constant c. Or I guess in this case no integration constant c, because it's a definite integral. Rebecca says, bro wears collared shirts to bed. That is not true. You are spamming the 100 emoji for yourself. However, if you gave me a PJ set with a collared shirt, I wouldn't stop you. Alright, let's type this answer in. I'm not going to say it out loud as I type it because you've heard me say e to the negative 10x more times than you should ever have to. There are two of you spamming the emoji. That's good to know. Thank you. Keep doing that. Unfortunately, it seems that that answer is incorrect, which means we've made an error that has to be fixed. Yes, I know, very sad. The integral is incorrect. We have to keep going. All right. We have 13 minutes left in this session. We're going to take it from the top and try this integral again. Rebecca, please stop asking questions about my nose. That is scary. But also, I don't know. I think I do have a mole next to my nose. But no need to point it out. Okay. So now we have the integral of e to the negative 10x times cosine x dx. Let's get to integrating by parts. So first, our general form is integral u dv equals uv minus integral v du. So let's go ahead and lay out our u's and v's. U is going to equal e to the negative 10x du equals negative 10 times e to the negative 10x dx. dv equals cosine x dx. V equals sine of x. Rebecca, please don't call me a mole in chat. I'm not rich enough to have mods. If I did, I'd say mods, ban that guy. Not actually. But let's get back to the integral. So we have uv, which is e to the negative 10x sine x, minus the integral of v to u. And v to u is going to be negative 10 e to the negative 10x sine x dx. Let's distribute the negative from that negative 10 to make it plus the integral of this thing. Very good. Okay. And now we're going to do this integral through integration by parts, where u will equal 10e to the negative 10x, du will equal negative 100e to the negative 10x, dv equals sine x dx, v equals negative cosine x. Rebecca Clark says I could convince her that I am bald and wearing a wig. I don't know what that means, so I'm going to keep going. E to the negative 10x sine x plus, you're going to have this equal u times v. So it'll actually be minus 10e to the negative 10x cosine x minus the integral of v du, which is negative cosine x negative 100e to the 10x, so that's just going to be 100e to the negative 10x cosine x dx, which is the same integral as before. So we are going to say well, it's plus 100, it's 100 of this integral. That if we add it to the other side, we end up with 101 times the integral of pi over 2, 0, e to the negative 10x cosine x dx equals e to the negative 10x sine x minus 10e to the negative 10x cosine x all over 101. And then what we're going to go ahead and do, because I think we're probably supposed to do it, is plug in our limits of integration into this function, right? So we are going to have e negative 10 times pi over 2 is negative 5 pi times sine of pi over 2. Sine of pi over 2 is 1 minus sine of pi, or cosine of pi over 2 is 0. So this term is going to cancel initially. So it'll be minus nothing, actually. Rebecca says she's going to make me do the DI method later. I refuse on principle. So we're 101 minus the second term when we're evaluating a 0. Sine will cancel to 0. This one will not. So we'll end up with minus 10 times e to the negative 5 pi all over 101, which equals negative 9e to the negative 5th pi over 101. What a gross equation, truly. Well, actually this is wrong. Hold on. Because it should be minus 10e to the 0, which is 1. So it's minus 10, not 10e to the negative 5 pi. Okay. And then it's minus negative 10, so we should get a plus. So we should have 10 plus e to the negative 5 pi over 101. And if we plug that in, that is indeed the answer. All right. On to the next question. Good God Almighty, what is this? Okay, this is one of those integrals that is, frankly, really scary to look at. I'm not actually completely sure what the eligible approach is here to get started. So let's think. 5x seems to pop up a lot, and it looks like we can rewrite to have a lot of square root 5x's in here. So let's see. This bottom, so we have tangent, arctangent, square root 5x over 5x to the 1/2 is just square root 5x plus 3/2 is just square root 5x cubed. So if we set u equal to 5x, du equals 5dx, so du over 5 equals dx, then we'll have the integral from 1 to 15, 0 to 15 rather, of the arctangent of the square root of u over u plus u cubed. Now, and oh, this is also, let's get a 1 over 5 in here. We'll write it in better than that. We'll just go ahead and, yeah, like that. We also need to rewrite our limits of integration. 5 times 1 over 15 is 1 over 3. 5 times 0 is 0, so it's 0 to a third now. So we're going between 0 and a third with the integral arctangent to the square root of u over u plus u cubed times 1 to the 5th. So this is still pretty nasty, but we can do some simplification that might make this a lot nicer. So, let's see. If we set a term equal to the square root of u, the derivative of that term is negative 1 over 2 square root u. and we don't have that in our integrand, so that's probably a bad strategy. So we're not looking at another substitution, at least not yet. So now we're probably interested in ways that we can separate out the function, kind of break things up. So let's see what we can do. We have two terms in our denominator, one plus the other. And that would only really be super helpful if we could actually switch the terms out. If they were in the numerator, they would be helping us out. In the denominator, they're not much good. So let's see if we have any trig substitutions we can do with our inverse tangent. Let me pull up my formula sheet. Arctangent. Even though it might get a little nasty, I'm going to see what happens if you set u equal to, or w equal to arctangent square root u. dw du, not dx, would be equal to u prime over 1 plus u squared, so we're going to be looking at -1 over 2 square root u over 1 plus u. So this is kind of interesting, actually. So that is -1 over 2 square root u plus u to the 3/2. That's actually looking really interesting. Hold on. Because then we end up with dw equals, or dw times 2 square root u plus u to the 3/2 equals du. That's all over -1, which just means we make this negative. Earlier, we said u equals 5, 6, so we should still have u square root here, and u to the 3/2 here, which means we're getting to 0 to 1/3 w over square root u plus u to the 3/2 times 2 square root u plus u to the 3/2 dw. This is all negative. Okay. This is actually tremendous. This is exactly what we wanted to do. I didn't really trust the approach, but math is trustworthy. I need to learn that. So now the trouble is actually getting stuff to cancel, but I think, what the heck is happening? Okay, there we go. This has actually gone exactly where we'd like it to go. The only problem is that 2. So that 2 is not too nice. So that's making the cancel kind of funky. Let me just check something. Yeah, okay, so the 2 is supposed to be there. But I think if we're careful about our algebra here, it looks like, let's write this out a little bit more clearly. Rebecca says, do you want me to sit in a dark room staring at this? If you're asking me if you're like held hostage watching the stream, that is not the case. You can leave if you like. If you'd like to stick around, you are equally as welcome. It's the same as -1, 2 square root u is 1 plus 4. And at this stage, we could multiply both sides by 2 and say that 2 dw equals... Okay, yeah, and I'm just going to finish mathing this out to make sure that it looks right. And say -1 over square root u plus u to the 3 halves du 2 dw square root u plus u to the 3 halves equals du. Negative, of course. Okay, so basically what we've just done is verify we can pull that -2 out, and we will finish this integral after break. So get up, stretch your legs, get something to eat, something to drink, see some sunshine. I'm gonna go pet my dog. Alright, accidentally let that break run on a little long, but we will get back to work. Alright, jumping right back into the question that we left off on. So we have the negative integral of 0 to a third, or from 0 to 1/3, negative 2w, I guess I already carried the negative 2, so 2w, square root u plus u to the 3/2 all over square root u plus u to the 3/2 dw. These two terms cancel, so that we get the negative integral of 2w from 1 to a third, or sorry, from 0 to 1/3. So that leaves us with pretty easy integral. We have from 0 to a third w squared, negative w squared, and of course we have to sub in our value for w, which is inverse tangent square root u. And since we adjusted our limits of integration, we don't actually have to substitute in our value for u. We're just going to go from here. Square root 0 is 0. Inverse tangent of 0, I believe, is 0, but let me double check that. Yes, that is the case. So this term will cancel. Square root a third, let's see if that has like a super specific value. It does not. So we're going to go ahead and plug that in. Negative inverse tangent of the square root of 1/3. Alright. And that is incorrect, apparently. So let's try a different technique. In this case, I'm going to try more immediate and larger substitution, going from integral inverse tangent square root 5x over 5x squared plus 5x to the 3/2. And we're going to rewrite this using u equals inverse tangent root 5x so the derivative there, it should be 1 over negative 2 square root 5x all over, let me check what that would be. To open the integration sheet, 1 plus, it's squared, so be 1 plus 5x. Which means after taking negative 2 out, we'll get du equals 1 over negative 2 square root 5x times 1 plus 5x dx, which means that negative 2 du equals 1 over square root 5x plus 5x to the 3 halves dx, which means negative 2 du times square root 5x plus 5x to the 3 halves equals dx. So we're just going to substitute that in, and we get negative 2u times square root 5x plus 5x to the 3 halves du over square root 5x plus 5x to the 3 halves. Obviously, these two terms cancel, and we're left with negative 2u du, or negative u squared from 0 to 1/15, which means we will have negative inverse tangent square root 5 times 15, or 5 times 1 over 15, which is a third. So square root a third, that's all squared. And then that's going to be minus, or plus rather, since we have a negative and a negative, inverse tangent square root 0 squared. And no plus c, since this is a definite integral. And then altogether, that is going to yield, oh, let's get this back up. How long has that been gone? So I'm just going to leave it in this form. Negative inverse tangent square root 1/3 squared, and we're going to see how that turns over. Alright, I'm going to try this integral again one more time. Unfortunately, this one is not going super well, but when calculus is beating you, you just keep going. Alright. And with that work session, that will conclude this afternoon's stream. So we'll probably get back on in an hour or two, but I am going to go get some food, and anyone watching, recommend you do the same. Take a good break. Best of luck with all of your studies.